or do you want to do like some sort of
the moderator will start, and then there will be a speech from Prof. Fitria, and then after that you, yeah, please Aci.
Okay.
Oke, Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirrahmanirrahim.
Waalaikumsalam warahmatullahi.
Kita masih diberikan nikmat yang sangat luar biasa pada hari ini. Kita bisa berkumpul semuanya dalam keadaan sehat walafiat and healthy. And then terima kasih banyak pada para partisipan yang sudah hadir, Bapak Ibu dosen baik dari UNS maupun dari universitas lain. Ada Bu Yuni, Bu siapa lagi tadi ya? Oh, saya kurang lihat satu, mohon maaf. Untuk membuka acara pada hari ini, mungkin terlebih dahulu saya beri waktu dan kesempatannya kepada Profesor Fitria Rahmawati untuk memberikan opening speech sedikit.
Ya, thank you Aji.
Ibu.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Yeah, Alhamdulillah, today we have an international guest lecture on heterogeneous catalysis with an expert from Leipzig University. He is a postdoctoral fellow in catalysis, Dr. Michael Kuppel. Thank you, Dr. Michael, for your willingness to be our guest lecturer today. And then this event is actually our 6th guest lectures, because we continue to arrange such kind of guest lecture event. And then, of course, for me as a chief of master degree in chemistry, I'm very glad to know the enthusiasm of students as well as the lecturers. And chemistry department will always facilitate all of the effort to develop network between academicians or between researchers, whether from Indonesia or from abroad. And the network in chemical education or in research and publication. Because I believe that this kind of event will increase also the recognition of our department as well as 11 Maret University. Because through this event we can invite college from other university, or we can college whether undergraduate student or graduate student from other university, and then college lecturers, researchers from other institutions, and then we can communicate each other, discuss some specific topic together. So yes, this kind of event is very useful, and because this is a online event, so there will be more flexible to be conducted. Thank you to Dr. Ernat Witri Wahyu Lestari, who arranged this event very well, and to Rigito Cesario, our alumni, also arranged this event and communicate with Dr. Michael to be willing to be our guest lecturer today, and to all of the students who prepared this event very well. By saying Bismillah, I open this event. Have a good day, joyful discussion, and enjoy the meeting. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Well, thank you to Professor Fitria Rahmawati as our head program department of chemical master program. Thank you for opening speech and also for a guest lecturer. Okay, always giving us opportunity to learn, especially today. Also with us, Michael Guppel, Dr. Michael Guppel. Hello, how are you today?
Good. I'm good. Looking forward to the presentation.
Yeah, Dr. Michael Guppel is our guest lecturer today, and I would like to read a little bit of his curriculum vitae. He has come from Institute of Chemical Technology, University of Leipzig, Germany, and his main research interest is heterogeneously photocatalyzed sunlight-driven CO2 upgrading, and then heterogeneously catalyzed upgrading of biomass-based substance, and also mass transfer limitation in heterogeneous catalysis. It's very interesting. Heterogeneous catalysis is a very interesting area. Of course, since it has been used widely in many areas of industries. So there is 29 participants. Maybe we will start. We can start. Dr. Witri.
Yes, just start.
Okay, let's start. Is everything ready, Dr. Michael Gupel?
Yes, I think so. Everything's ready on my side.
Okay. I think the screen is yours. Please.
Okay, thank you very much. I assume that you can all hear me well. If not, then you may just speak up. Yeah, you may also speak up during the presentation, I guess, if there's any questions. I mean, at least this is like a familiar audience or like a small audience so that we can like communicate with each other during the talk, I think. I will just use a couple words to introduce the city of Leipzig, which is, of course, as you may or should know, located in Germany. Maybe you don't know so much where it is in Germany, so I will give you some help here. This is where Leipzig is located, so it's a bit south of Berlin here, and even more south than Rostock, where the Likat is situated. And yeah, it's in the heart of Germany, in the state of Saxony, in the city of Leipzig, which has like 600,000 inhabitants. I know, I think, it's still growing strong. And of course, it's a very nice city, as evidenced here. You can see the old buildings. It has like a quite rich tradition in culture and in science. And I will, of course, focus more on the science part today. With that, of course, I will also talk about the Leipzig University. This is the central campus as it looks today. Of course, it doesn't. Of course, this has been modernized recently. There's this big Polyneum here, which is like a combination of a church and like a conference room, which is very nice, and also some art is displayed there from the long tradition of the university. If I talk of long traditions, it's actually really quite a long tradition. So the university was founded in 1409 and is operating till now. That makes it one of the oldest in the world and the second oldest in Germany. And there have been like rather famous people living and studying here. I'll just name Wilhelm Ostwald, of course, is very interesting for us as catalysis scientists, who's working here in Leipzig. Heisenberg has been working here, Debye and Hückel, you may know from physics and theoretical chemistry. And of course, also Angela Merkel has been working here as a scientist, the still Chancellor of Germany, probably not for long anymore. So that is basically all the words I wanted to use about the city of Leipzig and the university. I will also just give a very, very short introduction on the topic of sustainability, because I think this is like rather common knowledge among chemists these days. So I will use a bit of an unusual maybe graph to introduce you to it. And also you have to forgive me for the rather unscientific labeling that's called importance here on the y-axis. That's of course not a very scientific measure, but it's just used for illustration. And what I want to illustrate here is the use of renewable versus fossil resources over the course of time. Because nowadays, of course, we're struggling to replace our fossil resources and fuels with renewable ones. But and the question arises, is it even possible, and can we run an economy on that? We shall not forget that in the past, of course, we basically exclusively used renewable resources because we didn't really have access to fuels fossil ones. Or even all the way back to 1409 and beyond, renewable resources like wood would make the basis of our economy and industry. And of course, this has developed, and so have the demands on the renewable resources and the products we can make from them. But still, it should be not impossible for us, at least, to maybe switch back from fossil to renewable resources. And you could really say switch. I know this will be like a challenging task. It will demand a lot of technological and political effort to do that. But I think it should be possible. And us as scientists, we should try to work to enable society to get there. So what am I going to talk about as the title and analysis? It's going to be about polymer precursors and sustainable routes towards them using heterogeneous catalysis. And to do that, I will basically make 3 more or less case studies of work that has been or is done in our group on this field. So first, I will basically separate these chapters according to the resource, the renewable resource that we get. That's basically used as a feed for our reactions. Basically, it's the reactant to get our. The first will be glycolic acid. We will talk a bit about the influence of support material studies in the conversion of glycolic acid that we have done. And then this glycolic acid comes from algae-based solutions. The first part is about converting model solutions and learning something about basic scientific facts and influence of the support material. And the second will be more application-oriented in converting real algae-based solutions, which comes with an additional set of. The second will be about plant oils and especially epoxidation of fatty acid methyl esters. There we use TS1, then zeolites as catalysts, but we use them not alone, but in composite material with some spherical activated carbon. We will talk about the influence of absorption in these kind of reactions, diffusion, and also briefly touch a synthesis field we have recently been venturing in, that is towards the synthesis of micro and macroporous TS1 catalysts. Finally, I will just briefly talk about thermocatalytic reforming of bio-oil, TCR. It's a project we are involved in also together with the Fraunhofer Institute. It's rather in its infancy, so I will just give you the general scope of the project if there is enough time for that. Okay, let's jump right into it. Each chapter will have its own little introduction. That's why also I don't have a big introduction at the beginning. And I will just start with the glycolic acid. Of course, all these works are not done by me, or at least not exclusively. I try to help, of course, but most of the lab work was, of course, done by our dear students. This one was mainly conducted by Florian Hart, who is now working at the Slovenian Institute. So glycolic acid is this molecule that you see here. It's basically a C2 acid with a hydroxy functionalization. And it is an important building block. We will come to that later. But first, of course, we will say, okay, where does it come from conventionally? How do we make it based on fossil resources? We can do a hydrolysis of monochloric acid and come to the glycolic acid. And we can do the carbonylation of aldehyde. Of course, these always require these substances from fossil fuels and resources, and we want to avoid that. That's quite clear. So our aim is really to move away from the fossil resources and come to biomass utilization. And we're not the first ones to try this. There have been research groups working on this. So there are processes based on renewable resources that will also enable us the access to this glycolic acid. That is, for example, possible via using cellulose. So here is like a rather complex reaction scheme. I don't want to highlight that in detail, but you can see that you can start from a biomass-based resource like cellulose. And cellulose is also, it is considered to be a non-edible biomass. You know that there's also this discussion going on between using biomass that is edible and non-edible, and the question of first and second generation biomass products and fuels. Of course, our aim should be to use non-edible resources to not compete in the production of chemicals with the nutrition of the people of the world. So this is something that can be done. You can see the catalyst here is maybe not the environmentally friendliest that you can think of. But it's a process that because of access to the glycolic acid based on renewable resources. So why don't we just use that? Well, there is some drawbacks to this conventional approach of using biomass. And the conventional approach usually involves that you take the biomass, you grow it on a field, you harvest it, you process it, you transport it from A to B, and finally you will get a product after some chemical conversion. But this has a lot of disadvantages because you have to regrow it afterwards. You have all these processing and transport steps in between. So this concept of green chemistry, although it is green, does still have some drawbacks. And we are working together with a partner in the University of Leipzig and the Institute of Plant Technology, who tries to introduce a different concept of chemistry, green chemistry, which he calls a new green chemistry. And it basically involves not growing plants and harvesting them. Yes? Is there a question? No? Then I will just continue. It basically involves not using the sunlight to grow plants, harvest them, refine them, to do some fermentation process to finally come to a product, but rather use algae biofilms, algae themselves as microbioreactors. Basically, the algae, they are not being harvested, but they are producing our desired chemicals and excreting them into the surrounding medium, so that we don't need to harvest them and regrow them, but they can continuously produce the desired biomass resource. This also gets us around the problem, which I don't stress so much, and I don't want to, but we shall not forget that photosynthesis, although it's much more efficient, anything we can do with semiconductors in the field of photocatalysis, which I'm also working on, so I think I know what I'm talking about. Artificial photosynthesis is very hard to achieve, but also the natural photosynthesis is not a very efficient process. So whenever you use the energy of the sunlight to grow your plants and then harvest them and so on, you always lose also a fair bit amount of energy by all the metabolic things that the plant needs to do and inherent inefficiency of the process. Okay, so what does this mean in the context of our? We are using microalgae, CO2 and sunlight, to produce glycolic acid, which is basically an intermediate of their metabolism. And this glycolic acid is excreted into an aqueous medium. So we don't need any cell harvesting. We can have a highly selective process, and we have no net nutrient consumption. Of course, we need to provide these algae with some medium so that they can grow, and that will be addressed in this part when I'm talking about the conversion of the algae-based solutions. Yeah, it is still a no net nutrient consumption process. So what we are getting from our partners is a diluted aqueous glycolic acid. That's what the algae medium gives us. And of course, now our task as heterogeneous catalysis scientists is to make something out of it. We decided to go for ethylene glycol, and that is what the title of the presentation also suggests. This is a precursor for polymers, to make polymers out of them. So we are trying to investigate this second step here. We're taking the glycolic acid, we're taking a supported metal catalyst, we're taking hydrogen usually, and we're reducing it to ethylene glycol and or maybe. So that's what we're going to talk about in this presentation. Glycolic acid in principle, and that's the beauty of this process, giving us glycolic acid, is an interesting platform molecule that you can move from to a lot of different chemically very interesting species. You go oxidation to oxalic acid. You can also go the reductive route to acetic acid and ethylene glycol that we have decided for. But I think in general, this concept of new green chemistry giving us glycolic acid is interesting because this glycolic acid can be a platform chemical towards many other molecules, and they will all be derived from renewable resources. In fact, we only use basically so that's very interesting. But again, we are focusing on ethylene glycol. Why do we focus on ethylene glycol? Because that is a stepping stone towards. How do we do that experimentally? That's actually a rather low-tech approach. At the end, I will also show you a more high-tech apparatus that we're also having. We're having like a huge scale of catalytic testing apparatuses from high to low pressures and high to low temperatures. This is again a rather basic case. And here are the reaction conditions. So we're running with 150 degrees Celsius at not super high, but somewhat elevated pressures of 40 bar of hydrogen. That's for the reduction. You have to imagine we're doing this in aqueous solutions, and of course the solubility of hydrogen in water rather low. So to have a high concentration of hydrogen in the aqueous space, we need quite high pressures. Just remember Henry's law. Yeah, that's just illustrative for you to see how we do the experiments in which setup. Now I'm going to talk about the first specific chapter. And what we did first is study the influence of support. So how did we do that? Yeah, it's a basic like empirical approach. We did a lot of ruthenium as active phase. We screened before. I did not show the results here. Ruthenium was by far the most active. The active phases of the metals that we screened. We screened a couple noble metals like platinum, palladium, non-noble metals like nickel. Ruthenium was most active. That is not super surprising. That is known from literature for these type of reactions. Doing aqueous phase, biomass phase conversions, probably looking for ruthenium as an active good idea. It's known to be very active. It's not even 100% understood why that is the case, but it's known to be rather active. So we settled for ruthenium. We used a ruthenium on carbon commercial catalyst that is stand here, the name of which is here. And we also did a lot of in-house preparation of ruthenium-based catalysts on different supports, activated carbon, sulfonium, titanium, silica, aluminum oxide, and zeolite wire in the H form. What you can see on the y-axis is the conversion of platinum gases normalized to ruthenium. So we should never forget that if we give such quantitative measures of activities of the catalyst, it is always a good idea to normalize to metal content. And that we did here, and we do have ICP-OES analysis available to check for ruthenium content, and we normalize the conversion by ruthenium. And what you can see here is a bit of like a non-clear picture, I would say. So we cannot really say there is a clear trend here already. We see that titanium seems to be rather good. Carbon also, silica, alumina are so and so. What we wanted to investigate in this study, first we can also look at the selectivities. The selectivities are also like quite out and out, I would say. There's no clear trend to be seen here. It needs to, however, be pointed out, we can only really detect the products of the phase. So we are lacking like coherent gas phase analysis, quantitative gas phase analysis for these type of reactions, which is a bit sad, but we can close the mass balance in cases of good catalysts, I want to say, like with high selectivity to about 80%, but we are still lacking some of it to close the carbon balance. Again, there is no clear picture. We wanted to investigate what makes the support a good support in case of ruthenium as active phase. What is the scientific reasons for the catalyst performing the way it is? So first we looked at specific surface area, and with that also metal dispersion. And that you can see here. The blue bars are basically giving you the specific surface area of the catalyst, and the red bar is giving you the active metal surface area. So basically speaking of how well dispersed the metal is in the catalyst. You can see some things here. The first thing you can see here is that the industry knows how to make well-dispersed catalysts, and there is an art that they are selling to you in form of their catalysts, which have high dispersion. And that is very good. If we try this in-house, we are not as successful, but that is also not the point here. The point is this study is not to make a very well-dispersed catalyst. It's to understand the effects that the support has on the catalyst. And we can see, and that is also not surprising, if we have a rather high dispersion, a rather high metal dispersion, we also see comparably high activity, like in the case of the commercial catalysts. Also, that is true for ruthenium, which is somewhat well dispersed and shows the highest activity. But you can also see that there is a not very well dispersed catalyst, like the ruthenium on zirconia here, this one, which also performs very well. So although the dispersion, which is usually the case, is an indication of activity, it does not explain it all. There must be more than just the dispersion of the metal. So we continued looking, again, the same is true. I don't want to mention this in every single case. What we did also look into and investigated into is the acid site density. For this, we have the temperature programmed desorption ammonia available. That is a technique that can give you some statements about acid site density and also about acid site strength, but we didn't investigate this here too much in detail. What we can say here is that if, for example, look at the ruthenium on the zeolite Y, we of course expect it because it's tends to be rather acidic, and so it is, but it is not very dense. So it seems that the poor acidity, which in literature sometimes is mentioned as an important contributor to activity, does not seem to be showing, it does not seem to be significant for high catalytic activity. And we did also investigate the core system. I did not show it here. Also there, we found no clear correlation between texture properties and the activities. But last but not least, we investigated the reducibility of the material. For this, we have temperature programmed reduction available, which again is a technique that can give you an idea about the amount and the type of the reducible species that is on the catalyst. And this again looks a bit confusing. But of course, it is the task of the scientists to make the confusing data look more straightforward. So we investigated it a bit and thought about what could be a good descriptor of activity. And what we found is actually that if we take the maximum of the reduction temperature, basically showing us how well the species can be reduced, and plot that versus activity, which is determined here as phosphoric acid conversion normalized to ruthenium content, as we can see somewhat of a code. So we assume that the support material influences the reducibility of the ruthenium catalyst, and that is understood. It can be done via metal support interaction, and that the facile reduction of the ruthenium correlates with high catalytic. So as a short intermediate summary, I have this at most of the chapters. Ruthenium exhibits the highest activity at phase. That is known from literature as well. The dispersion is important. That's also to be expected, but it's not all. Acidity and pore system or texture properties show minor influence of activity, and the reducibility of the ruthenium species on the support seems to be a key factor that affects the catalytic activity. And you can influence it via the support. So that is a short chapter we did about the influence of the support on the activity that set conversion. As a second chapter, we investigated, and I should say that maybe state that also before, we did really not use the solutions that come from this type of process, because they contain not only aqueous glycolic acid, but also other things that are needed in the medium to keep the algae alive. The study before we did based on model solutions which contain only water and glycolic acid in a concentration, of course, that is representative of what this process looks like. Now we want to move away from that, so away from our model aqueous glycolic acid solutions, and we want to do that by, and if we do that, I should maybe point that out first. If we just take the algae solution and apply our catalyst in our best conditions before, we see basically no conversion. So the system is bad. So we can do that for model solutions, which is nice. But of course, we eventually want to move to the real system, and that is more complex, and high conversions cannot be. So what we did, we wanted to systematically study the influence of the different components that are in the real algae medium. And I broke it down to three main culprits or points of investigation that are in the algae medium, which are nutrient salts for the algae to live, which is a buffer solution that the pH which is a buffer that the pH in the solution remains constant, and due to the process, we need a metabolic inhibitor, basically telling the algae to not consume the glycolic acid into its metabolism, but to rather excrete it into surrounding medium. So this is also something that is needed. We take all these components and individually add them to the glycolic acid solution to see their influence, their single influence on the whole process. So, and for this we use the ruthenium on carbon catalyst, the commercial one that has also been. So what did we find? So these pictures are a bit more busy, or the slides, so let me walk you through it. So the black point always indicates the base, basically only glycolic acid solution. So basically what we have investigated before, the model solution. And here we add some salt and some acids to adjust the pH. I should also point out that if we take the solution as we get it from the algae process, the pH is somewhat new. It's a very high pH, which is needed for the algae to, if they cannot operate at these low pHs, which would form, if imagine during the process you constantly are producing an acid, the glycolic acid, do not buffer the system, the pH of the whole solution will shift towards very acidic mediums, and the algae will die. So there is a buffer in it, and if you take the solution that is been buffered, the pH is somewhere here. And one of the reasons why this does not work, why we don't see any conversion here, is that we need to adjust it. So we did do that and adjust the pH, and what we find is if we adjust the pH, the value which is about the value of the aqueous glycolic acid solution, we get very high conversion. And we assume that this is the case because there is an equilibrium between the glycolic acid here and the deprotonated form of the glycolic acid. So we just abstract the H here and have a negative charge here, which you of course get at higher pHs. And this this glycolate form of the hydrogen is probably less reactive. So we need to adjust the pH. And we found that H2SO4, because it gives us comparably high conversions that are very close to the model case, is the best acid to do. Then we also investigated the influence of buffers. Again, only single-handedly adding each one of the buffers to the aqueous glycolic acid solution and see how the conversion goes. And if we add this buffer, the MES buffer, we can see we have quite a drop in conversion. And we can also add different buffers and see how the conversion goes. So what we can already do here is we can give a recommendation to our friends in the plant physiology department to which buffer to use in their biological conversion to least hinder the subsequent conversion via heterogeneous catalysis. We would rather like them to use this type of buffer. And why do buffers have this negative influence on the conversion? It is assumed or also known from literature that, of course, sulfur-containing components, but also nitrogen-containing components can go to the active sites and irreversibly bind on them and deactivate it. And the last thing that we investigated, or that I want to present here, is the metabolic inhibitor. We talked about that. This is this EDA. It's a very complex organic substance, and it's needed to ensure that the algae excrete the glycolic acid into the surrounding medium and don't use it for their own metabolic. And what we can see here, this is also very low concentrations. You can see here, and the star here indicates the concentrations which are in the algae medium. This is basically in the algae medium, and you can see that the EDTA, which is also used there as a complexing agent, is not a big influence, but the metabolic inhibitor, because it contains multiple sulfur atoms, is a very strong deactivating agent for the subsequent catalytic process via ruthenium as an. So we can give a recommendation to our friends that to use as few as possible of that, or to maybe try and switch to another type of metabolic inhibitor, because this is already at very low concentrations. You can see this is millimolar scale here, and we're in 0.01. So very low concentrations of this already severely hinders the technique. However, what I also want to give you, I said, no, okay, this is all detrimental and these are bad effects, and we're trying to understand that, and it's an important contribution. We need to know if we ever want to move to conversion based on biomass-based solutions like these algae solutions are, these glycolic acid solutions from algae are, we need to know what the components that are naturally in biological solutions and components, what they do to our catalytic steps that we do after we get the solution. So that's very important. We contributed something to basic understanding there, but of course we were also eager to optimize our reaction. And here you can see the summary of what we've done here. So again, this is the only glycolic acid solution case. And this is if we use all the additives that are in there except for the metabolic. Then we are still okay. So the metabolic inhibitor is really the main culprit in reducing our catalytic activity. So this catalytic activity is not super impressive, but it's something to work with. And if we then do something to the algae solutions, for example, this is a better, so to say, algae solution, which has a modified nutrient medium, which takes into account some of the suggestions, what to add and what to not add. And we can see that we get much higher activity, especially also if we prolong the reaction. So we can then move to at least 90% conversion to selectivity, so it's still something. Okay, so again, short summary. The pH of this algae needs to be adjusted prior to a catalytic reaction, because if it comes out of the algae selection, the algae solution, the pH is buffered to around 7 for the algae to live. We need lower pHs, however, to get the protonated form of the glycolic acid. The main contribution for reduction catalytic activity is the inhibitor. But also the addition of salts and complexing agents and buffer are detrimental. You can also imagine, if we're talking about salts, every inorganic salt you put in such a solution will decrease the solubility by the salting out effect. And this is, of course, detrimental because we need high hydrogen concentrations for the reaction to. But if we adjust the reaction conditions, we can achieve at least GA conversion of algae-derived solutions, so real solutions. And we're still at low selectivities, however, what we're working towards maybe making this a viable industrial process in the future. Okay, this brings me to the second big chapter, which is dealing with epoxides from plant oils, meaning we are taking plant oils as a raw material, basically, and this work has been carried out by Alvin Osorio, who is still a PhD student in our group. So if I say we're taking plant oils as a raw material, we are not doing the first processing step, and that is usually the kind for what we do. We are not so much experts in the direct conversion of the biomass as it comes from the field or from the algae. But we are usually considering ourselves as experts in the subsequent catalytic upgrading of these of the substances obtained from the raw materials, which are usually some sort of platform. And this is also the case here. So we take our plant oil, which has this type of substances, and then esters basically can then undergo a trans-esterification to get this fatty acid methyl esters. And this is basically the raw material we're looking at in this. This is the reactant basically we're looking at in the study. And what we want to do as a reaction is the epoxidation of this double bond to the epoxide. And because this epoxide can be used in 12 different applications, and amongst them are again polymers or polymer precursors, but it can also be used in a lot of other things. And it, of course, has a sustainable source. Although we are referring here to the conventional type of biomass harvesting and but still, this is an attractive concept, and that is something that has been also more or less established in the scientific community and also partly in the industry. So how would you carry out such an epoxidation reaction normally? You could use the Kuliah reaction. Sorry, my Russian is not excellent. How do you do this? You take your substance to be oxidized, you treat it with some kind of air acid, you get an intermediate state, and at the final you get a. Why is this not very green and not very beneficial or not very good reaction in general? You have to handle the pear acid, which of course is very explosive, as you may imagine if you see some chemical structure like that. B, you need stoichiometric amounts of this per acid, and the acid you get out of this part because it's just an unwanted step product, and it is an acid, and it leads to an acidic medium at the end. This acidic medium may be very detrimental to this reaction itself because it may lead to side reaction. Now, if you have a very acidic medium, you could cleave this epoxy bond again, and also in subsequent reactions, it's not very desirable because it may lead to unwanted side reactions. And of course, also acidic media are always like harder to deal with concerning apparatus. So, what are alternatives to making this kind of Kuliah reaction? It's using titanium containing silica materials that are like known to be good in epoxidation reactions. You can use the titanium beta zeolite. You can use materials like titanium MCM41, and catalyst also very much into investigation in epoxidation reaction. Meaning basically it's a titanium containing silica like one, where some of the titanium ideally or isomorphically substitute titanium, take some of the silica sides and put titanium there. Usually you get also extra framework titanium, so it's not only sitting on the silica positions, but ideally it is. However, also this catalyst has some drawbacks. Otherwise, we can just use it as is. And the drawbacks are that so it has very small pores in the range of 2 nanometers, and this of course leads to problems in mass transfer and accessibility, especially if you consider the size of our molecule you want to react with it. This is a rather bulky organic molecule. It can never enter the micropores of so we have problems with mass transfer and accessibility there, and also hydrophobicity is an issue because this molecule, again, is like rather hydrophobic. And due to OH on the surface, the PS1 may not be. Also, of course, we want to use H2O as oxidizing agent. Okay, so what material class did we then settle on? It is a combination of a PS1 and a polymer-based spherical activated carbon. Polymer-based spherical activated carbon basically looks like this. This is actually a picture that already has some TS1 on it, but this is basically also the synthesis strategy. So we want to take a bead of these kind of polymer-based spherical activated carbons, which are just abbreviated as spherical activated carbons in the time to come, and we want to carry out a TS1 synthesis in the presence of these carbon balls, let me call them, or spherical activated carbons, with the aim to embed the TS1 into the pores of this also porous carbon, porous activated carbon, and also of course. The advantage is that these carbons are commercially available. They have spherical morphology, which makes modeling or model investigations very, very interesting. They already have a continuous pore system, and if you want, you can in principle also completely remove them by calcination. And yeah, as I said, we wanted to use the SSC as a support or exotemplate for the TS1 synthesis. We're carrying out the TS1 synthesis in the presence of these what we get there is additional sorptive properties. So we have higher surface area, especially also the higher outer surface area. So the idea is to finally disperse the TS1 particles, because we know that we cannot get into the interior of the TS1 particles. So we can only use the external surface of the TS1 particles. So we want to disperse them as good as possible to get as much external surface as we can. But we will talk about this in a minute. This kind of extension of the surface area, and especially the sorptive, additional sorptive properties that you get from the spherical activated carbon may also pose some difficulties and challenges. Also, because they are commercially available and you can do some treatment to these activated carbons, you have a somewhat tunable hydrophobicity, which is also interesting for our studies, because we said before hydrophobicity is a key factor in activity. Okay, what is the case studies that I want to present you here? First is the influence of absorption. And to to understand what's going on there. Again, short like schematic on how the synthesis works. So we have the tetrapropyl ammonium hydroxide here. We have the titanium precursor and the silica precursor, and in presence of the water. This is basically our template. This is our silica precursor. This is our titanium precursor. And we do this in aqueous phase, and in the presence of these spherical activated carbons, we do a TS1 synthesis. And then we get out conventional temperatures that are also known from literature. And then we do some calcination, but not such high calcination that we actually remove the carbon, but just to get rid of the template. And what we end up with then is these kind of structures here. You can see that the white spots here are basically the crystallites of the TS1. If you magnify bigger, you can see that there are TS1 crystals that are actually sitting on the surface of these carbon activated spheres, and we did additional investigations with TM tomography, and we have strong indications that these TS1 crystallites are not only at the external surface of the spherical activated carbon, but also within the pore system of the spherical activated carbon. Again, a reminder for you, this is not a solid pore basically, but it's a pore system by itself. It's basically an activated carbon that has a pore system. Okay, so this is how the synthesis works, and this is what we end up. TS1 embedded in or as a composite material and with spherical. How do we do this reaction? Also, this is our low-tech catalytic reaction. So we do it at rather mild temperatures of 50 degrees C. This is the reaction we are carrying out. This is the abbreviations that are also going to be used in the future. So MO standing for methyl oleate is the reactant. EMO, basically the epoxidized form, is the product. And we're using H2O as a why is it maybe interesting or important that I tell you that? This basically, in this type of reaction, right, we just do a glass-glass catalytic reaction. We have easy accessibility to add different modes of starting the reaction, because we can really add our substances during the reaction. That's not so easy if you work into a pressurized vessel, where it's not so easy to at any time just add some reactants or some components, because yeah, you have a pressurized vessel. But here we can do that, and that enables us to two modes of starting the reaction. This may sound confusing right now, but I hope it becomes obvious why we do this in the next step. So we can start the reaction either by putting all of this in the glass and then adding the catalyst, or via putting the catalyst and everything already into the reaction mixture and start the reaction via adding H2O. So this is what we get here, and I will come to this term here on the y-axis in a minute. Basically, you could say like this is the reduction of the methyl oleate of the reactant in the liquid phase. So we start our reaction here, and it seems like, oh, this is nice. We have some reactions. We have different catalysts here, but this is actually very misleading because what we did here in this first part is just an adsorption experiment. So we added the catalyst, and we added the catalyst and the reactants. I think there's a person here. Thank you very much. So what we did here is it seems as if we have catalytic reaction, but we just put the catalyst in, and the reactants not even in the system, and we see a reduction of the concentration of the reactant. And we think like this is conversion, right? We're consuming our reactant, but that's not what happened. What we actually see here is only adsorption. That is something we need to consider when we make catalysts that have such a strong adsorptive functionality. The composite material, for example, like this. We think we see reaction here already, but what we see is adsorption. So we used as a term, which is a bit clunky, I admit, but we didn't come up with a better one, the term apparent conversion. And what it kind of describes is the concentration or the amount of moles of a reactant at a given time compared to the initial time. So it basically describes the reduction of the concentration of the reactant in the liquid phase. And this can be due to reaction as desired, but this can also be just due to adsorption. And that's something we need to be very careful of if we want to investigate catalysis in these type of systems. We need to make sure that what we look at is actually reaction. And so here we designed the experiment like this, that we stir the solution only with the catalyst and the methyl oleate, but not with the second reactant that is needed for the reaction, the H2O2. So here we add the H2O2 after some sort of adsorption equilibrium is established. And then what we get is a reaction. So here you see different catalysts that we investigated. We investigated pure TS1, we investigated TS1 and spherical activated carbon as a composite that is indicated by this dash here. And we investigated the same amount of both of the substances as a physical mixture. So basically not making a composite, but just physically mixing them together and see how they. So you can see if we make this composite material, we do get more adsorption, of course, because we add a lot of spherical activated carbon, but also we do get better reaction. But for now, it seems as making a composite material and simply making a physical mixture does not give a big difference. And that would be kind of sad. Making a composite material is some sort of effort. If you could just take the substances and pour them together and get the same catalytic results, that would be kind of sad. But it will turn out it's not exact. Because here we can look at apparent conversion. Again, that's the term I introduced before. So basically telling us the reduction of the methyl oleate in the liquid phase. But here we also look at the molar amount of our product, epoxidized methyl oleate formed per titanium site. And that is basically in the blue color. So we can see if we take pure TS1, we get a certain phase conversion. If we then make our composite material, our conversion, the gray one, is very much increased, and the conversion is also very much increased for the physical mixture. But the kind of what we would normally maybe call a selectivity towards the desired product is much higher for the composite material, indicating to us that there is a true synergistic effect in making such a composite as compared to a physical mixture. And as some control experiments, we also did use only the spherical activated carbon and silicate 1 spherical activated carbon composite materials, as well as pure silicate 1. So basically, these three species do not contain any titanium. And as expected, we also do not see any product formation. But what we do see is this kind of apparent conversion that only comes from adsorption. So we need to be very careful when we are investigating systems like this. But we can also say that we did increase conversion. So this again will be summarized in this slide. So unreactive adsorption can lead to a reduction of reactant concentration and somewhat like apparent conversion. So when we investigate catalysts like this, we need to be very careful to do a distinction between reaction and adsorption. And also you should probably do that, especially when you're using highly porous supports. You can see that if we go back here, already the silicate 1 contributes to quite an amount of adsorption. And this could be interpreted as conversion if you are not careful. I mean, it also always depends on the concentration of the reactant you take in your solution, but keep that in mind definitely. You could also go looking at the reactant product formation, as we have done here. We look at the molar amount of epoxy methyl oleate formed, but again, we are looking in the liquid phase. So we don't know about any adsorption that may be taking place of the product. So we may be also losing some product, actually forming more than we think, and just the product that is formed is being absorbed on the catalyst. So that is always something that you need to do when doing this type of reactions. But there's not only a warning, but also like a success here. So when we're making this composite, we could increase the activity, maybe about 4-fold compared to commercial TS1. And the increase in selectivity that we observe when we are comparing a composite material that we formed by our synthesis approach with a pure physical mixture by about twice. So the selectivity increases to 48 to 83% indicates that we have a true synergistic effect of making this composite. It ends up actually more yield of our result. Then I have a small case study of diffusion and TS1 composites. This is a bit of excursion into physics also, but please bear with me. So again, as a reminder, what kind of materials do we have? We have these kind of spherical activated carbons on which we have deposited and embedded silicalide 1 crystals. And these crystals are finally dispersed on the surface and also inside the material. And we can also do some EDX analysis that really guarantees us that we can see actually some silica on the EDX, and that tells us that this is really at least some silica species. And we will also confirm that this is silicalide 1 or titanium silicalide 1 later. And by additional experiments we also did with, for example, broken particles, we can make sure, and also some tomography studies, we can make sure that there is actually also crystals inside of the spherical. This is just kind of a check or a kind of for your understanding. So what we're doing here, and this is also indicated here in the sample labeling, we're making this composite materials here, and this number here at the very end indicates the mass fraction of the TS1. So how much TS1 did we put in? And now if you look at the nitrogen sorption, which is basically a technique that gives us access to the textile properties, so the adsorbed volume or relative pressure, you can see that, of course, if we take the pure spherical activated carbon, it's like a very good adsorbent. It's also a lot of nitrogen. There's a high pore volume. The TS1 is also porous, but very much less than the activated carbon. And now we're making these composite materials, and if we increase the amount of TS1 in it from 26 weight% to 56 weight%, we get a reduction in the volume itself. That is understood because we are adding something less porous to something more porous, right? So we're taking something very porous. You could imagine the volume of sponge, and then you add a stone to it, and then of course the volume overall goes down because the stone, it contributes some mass without being porous. And basically we have the same here. We have something very porous, and we add something less porous to it, and we get a reduced volume absorbed. But what we observe here is actually more than just a linear combination of these effects. So it's not only if we take half of this and half of this, we end up with an isotonic device in the middle, but the volume that is absorbed is actually more reduced because the TS1 is deposited in the pores of the spherical activated carbon and will block some of the volume to be accessible by this. This is also consistent with some mercury intrusion investigations that we carried out. And again, the effect of reduction in salt volume is more than a mass spectrometer linear combination. So from this, we kind of deducted a mental image or a scheme how this catalyst would actually look. And here you can see that the black stuff is basically the spherical activated carbon. The TS1 and the yellowish squares here are TS1 crystals that are deposited everywhere. So they're deposited on the surface and in the pores of the This is how we imagine our composite material looks like. Also, so you get some idea of the dimensions, and this is how we imagine it to look like. And this is probably like the most complicated slide, at least if you don't have like a strong background in physics. But please bear with me on this, because now we did investigations with a technique that's called pulse field gradient NMR, and that is basically an NMR-based technique with which we can analyze the diffusivity, the diffusion of molecules in situ, so basically in the reaction systems. We can look at how fast the molecules are diffusing in the system while it's basically more or less on the reaction. And we found that there's 3 different types of diffusion happening in this. One is a bulk diffusion that will always happen. So it's basically the molecules just flying around outside of the particle in the bulk, basically in the bulk liquid phase. This is the bulk diffusion of D1. Then we have intercrystalline diffusion. Again, remember the pores of the TS1 are too small for our reactant molecule, for the methyl oleate to ever enter into the silicalide 1 or TS and into the TS1 crystal. So it can only diffuse between the crystals. It will never go in because it's too big. So this is basically the intercrystalline diffusion. So we have agglomeration of the TS1 crystals, and in between the methyl oleate is swimming around. And the third type of diffusion is the diffusion inside the pores of this carbon material. And we can then see how likely it is that we find molecules in one of the three types of diffusion, or we could also say in one of the three surroundings or environments. So we can just look at the pure TS1. What we find there, of course, is bulk. This is basically only TS1, so not this picture here, but it's basically only such crystals agglomerated together. So we find, of course, a lot of bulk diffusion and some amount of intercrystalline diffusion, basically between the agglomerated crystals. If we just look at the carbon, of course, we again find bulk diffusion. It will always happen. It's outside of the pore system, and we find some amount of diffusion within the carbon. If we now look at the composite materials with increasing amount of TS1 content, we find that the amount of molecules diffusing between the crystals of the TS1 is increasing. So it's much more likely that the molecules are between TS1 crystals than they are in the bulk, or than they are in the pores of the carbon network. This can be explained, of course, with just having more of these crystals and the likelihood of a molecule being higher, but also with the fact that some of the pores of the carbon are blocked by the crystals, and so the methyl oleate cannot go. And okay, this was a rather complicated explanation of maybe not so straightforward. I hope you understood what I mean. So if we increase the titanium content, we get more intercrystalline diffusion, and more likelihood of the molecules to be close to the TS1. But we also decrease the overall diffusion speed of the whole system. Remember that we said, like, we have mass transfer problems. Usually the approach is that we want to speed up the mass transfer and by this get better reaction or higher catalytic activity. Here we're actually putting so much that if we decrease the diffusion, so the mass transfer goes slower. But if we look at the catalytic activity here, this is the lower weight fraction of TS1. This is the higher weight fraction. If we increase, it's only a small effect, but it's significant. It's outside the experimental error. What we see here is that if we increase the amount of TS1 and we, by this, decrease the diffusion speed, we still get more active. That's rather counterintuitive. We assume that this may be due to the fact that the catalyst, the reactants are just longer in contact with the silicalide crystals, because that likelihood of diffusing between these crystals in the intercrystalline room is higher. Or it may also be due to the fact that if they are in a vicinity of multiple TS1 crystals, that they are also have a more favorable interaction with maybe even multiple actives. Again, this is work in progress. We do not claim that we have fully understood that, but it's a very interesting finding. Okay, this is maybe the last chapter, and maybe I will skip the TCR process, but I will just briefly talk about this other strategy that we have. We said that a TS1 in principle is a good catalyst, but it suffers from problems of mass transfer and accessibility. And one strategy to circumvent that is to just make big ports into the TS1 that the mass transfer and the accessibility becomes better. And how can we do that? One strategy that basically, these are results from our own synthesis, but this strategy is based on a published one. You take some mesoporous silica SiO2 nanoparticles that you can also synthesize. The synthesis is rather straightforward. You add some titanium precursor to them. Let's take a look at these particles. You can just synthesize them. They are basically SiO2 particles that have a titanium precursor added to them, and they are really like very spherical. You can get them in very nice spherical shape, and then you do something that is called steam-assisted crystallization. It's like a bit more complicated synthesis route, and the idea is that you take this amorphous material here, the silicate and this SiO2 with titanium, and transform it via the steam-assisted crystallization into a crystalline TS1. And that works quite fine. And what you get then at the end is macro porous TS1. Basically, you have your TS1 material. That's basically the bulk of this material here. And this is basically all TS1, and you have this additional macropores in them to enhance the mass transfer and the accessibility. Here's also some TEM investigations on how these look like. Yeah, so you can basically see that they're basically these kind of spherical entities are kind of melting together into one bigger sphere and form this macropores. What we now did is compare these macroporous TS1 with micromesoporous TS1 that we have synthesized via different routes, for example, via alkaline treatment and pseudomorphism. We take always the TS1 that is macroporous, and we once combine it with macroporous with this synthesis approach that is rather new, and we also combine it with mesoporous via known synthesis approaches like alkaline treatment and pseudomorphism. So what we end up with is then a macroporous TS1 and two types of micromesoporous TS1s. So what we end up with is a macroporous TS1 and two types of micromesoporous TS1s. And as you can see on the left side here, from the XRD results, we do actually get TS1. All the crystalline reflexes are there where they're supposed to be. If you compare them to a commercial TS1 that is displayed in the bottom, yellow. And we can also see, I don't want to go too much into detail, that the pore systems are forming as we expect. We do have always the microporous pore system, of course, from the TS1. And some are having trouble with the cursor with the short stuff here. So we always have the microporous pore systems, and then we have different types of mesoporous pore systems. And we can also see that, of course, the initial system is already mesoporous, but we kind of lose this mesoporosity in the process of making the macroporous TS1, which is displayed here in blue. And what do we see? I just want to mention this briefly, is that if we again look only at the parent conversion, we don't seem to see any difference. Again, this is, makes us aware of the fact that we need to look into more detail. But if we look at the amount of product formed per titanium site, we can see that our macroporous TS1 outperforms the other. So actually here it seems beneficial. I mean, it's a different system, right? Before I talked about reducing the diffusion speed and actually getting more active systems. Now I talk about likely increasing the diffusion speed via formation of macropores, and with this increasing the catalytic performance. So it seems contradictory, but there is also very different catalytic systems that we need to know. So again, we do not claim that we fully understood that, but it seems that the addition of a macropore favors the selectivity towards the desired product, and it seems to create, it can either do that, maybe this is not a completely right conclusion point that I want to draw, that I want to bring across. So it can do that either via increasing the mass transfer properties, or it could also be that this is doing that because it creates titanium sites that are more selective towards the EMO format. We don't, of course, know exactly what we do to titanium sites. We do have some, have this in additional materials. We do have some studies about the titanium sites that we find in all of these catalysts, and they seem to be somewhat similar. But of course, we're doing different synthesis procedures, so the different activity may also result from different titanium sites and may not be exclusively attributed to the different pore systems. Okay, since the time is already quite advanced, I would like to ask the organizers. I have one small chapter about alkenes from TCR bio-oil that I could still show, or I could also directly jump to the. How is it with the time?
if you don't mind, maybe you can continue.
Okay, it's also it's a shorter thing because it doesn't contain so much scientific data that we've gathered yet. Because again, the project is more like in its infancy. But it's maybe also a nice approach. Again, we remember our general scope of making polymer precursors from renewable resources, and this is something that we do. That Felix Schmutzler, as a PhD student in our group carrying out the work, has done in cooperation with Fraunhofer Institute and a conglomerate of a lot of research institutions. And it's basically based on this TCR process. I will try to explain it by the video. So basically, you take some biomass and you add it to such kind of a machine here, and you basically heat treat it without oxygen. And what you get then out is some kind of biochar, and you get some vapors. And these vapors and the biochar are then further treated, and you get these vapors are cooled down. These vapor substances. And what you get out is some sort of bio oil. That's what's interesting for us, some water. And you also get some permanent gases that's actually containing methane that you can even use to kind of heat the whole system. So basically you can use the methane that you get out to make the whole thing running. And here you get some biochar that you can use as catalyst or as fertilizer. Run it again. This once. Because it was rather quick. So again, you add your biomass, you treat it without oxygen, thermally treated, and you get some biochar and some volatile substances. These volatile substances were further treated in this post-reformer. What you then get out is again gaseous substances that you can cool down, and when you cool them down, you get the bio oil. That's interesting for us, some water, and some permanent gases that you can separate out, or even sometimes use to fuel the whole thing to get. And also you get this biochar that can be used again as a solvent or as fertilizer, even has some catalytic. So again, we're talking about this bio oil. This is the apparatus as it looks in real life. It's not in our institute. It's in the Fraunhofer Umsicht Institute in the rural area. And what you get out is this TCR oil. And this is hydrotreated TCR oil. We are interested mainly in this. So this is more or less the basic stepstone for our investigations. But again, we're not doing this first process step. This is not so much our expertise. We're rather taking something that is coming from this first process step and try to see how we can kill it into a commodity chemical or a platform chemical or is needed in the modern. So what we do with this TCR oil, we do some distillation and extraction, and then we get out a fraction that is actually interesting for us, and that is the one we want to convert. You can see before we actually do the catalysis, there is a lot of reaction engineering and separation technology involved, but that's not so much conducted at our house. We have partners for that. What is the substance that we're working with? You can see them up here. This is basically the fraction that we get. And that's basically our task to convert them into this. Because these kind of unsaturated carbohydrates can again be used as polymer. So we have to actually perform two reaction steps. And here it comes where we also, I wanted to show you, that's why also I wanted to show you this. So we do also have like more sophisticated test apparatuses like this one here. So we have to do actually two reaction steps. We have a ring system here, so we need to open the ring. For this we use a zeolite and some gamma alumina and some metals. Use zeolite or gamma alumina as a support and some metals to get this ring opening reaction. Then we end up with these type of substances. So for this we basically need hydrogen. You can see, right, we hydrogenate the aromatic system here. And then we end up with saturated hydrocarbons, and then we want to dehydrogenate again to get the unsaturated hydrocarbons. So ideally we can use the hydrogen that is generated here to fuel this reaction, to kind of like get a more sustainable closed reaction system. For this we have like more sophisticated reaction equipments. You can see here, sorry for the German labeling. So this is the gas dosing. This is an HPLC. Here you can actually sample. Here you have all the electronics that you need for the apparatus, the GC. This here is actually the reactor. and here you have the evaporator. And then you need to perform this, and we need a different reactor setup for this, because you need also somewhat of a different catalyst and different conditions for sure. And this is maybe more simple, but it can be, again, you can see it's right next to the other one. It can be operated also with the same DC, and then you again have the usual components here of reactor and pump and separator. So I will just briefly mention the main challenges here of the first reaction step, the opening. What do we use? We use industrial catalysts here. So here in this project, we're not so much into the synthesis of catalysts. That was more a focus of studies I've shown you before. And we also consider ourselves somewhat of our specialty, that we do know how to make porous catalysts with different pore systems and then see how they perform in catalysis. Here we're actually using industrial catalysts. We are also doing some research on bimetallic catalysts, so we do actually do some catalyst synthesis. The challenges are the reaction conditions that we have to just deal with to get some activity. And this is like a real live feed, so it's not a model substance, so it will contain biological substances like sulfur. That is a problem for our catalysts, of course. If you look at the phases, you can already imagine that sulfur will be quite deactivating. And we are also struggling with unwanted side reactions. And of course, you can crack down these rather long chain hydrocarbons to short chain ones. That is not what we want to do, because of course this would decrease the value of the feed. So we want to just ring open, dehydrogenate, and not crack. And that is a somewhat tricky thing. Also, we want to have some control over the isomerization. And again, it's very complex that come from this bio oil. And what we eventually want to do again is this is our bread and butter. We want to vary some of the catalyst properties, and we want to see how they influence the catalytic activity and the product composition. And the things we're interested in here is the particle size, the pore width distributions, and the acidic properties, for example, of the catalyst. And for the dehydrogenation project, we are again using some industrial catalysts to get a benchmark where we need to go. And then we also want to do research with our own catalysts. Here, one of the main challenges again is rather high temperatures, and that you will have some severe deactivation via cooking. You can maybe imagine that. And again, we have to fight unwanted side and consecutive reactions, again in a rather complex reaction feed. And we also deal with the separation to some extent. And it's not so much our specialty, but it's also like somewhat on the scope of this. Maybe let me conclude. I don't want to make a very lengthy conclusion, because I had a short conclusion on each of the factors. When we look at polymer, of course, we know it's made up from a lot of different building blocks and monomers, so to speak. And we know that especially for polymer, and especially in these days, the whole thing can really be more than the sum of its parts. As Aristotle already said, if you make your polymer from a non-renewable feedstock, you will have a lot of problems. A, your feedstock will run out. B, the biodegradability of these substances is usually worse. So if we instead try to make our polymer from renewable resources, I think we can give like an important contribution towards a more sustainable society. And heterogeneous catalysis, as I tried to show you in these 3 base cases or study cases that I've presented, can really help us to start from some renewable resource and end up with something that can be a polymer precursor or any other, or maybe as a platform chemical, a lot of other commodity lives. Of course, all of this work can not be done without the help of a lot of people, scientifically, financially. Some of the people supporting us here are on the slide. Of course, also I have to thank Roger Glaser, my boss. He's a nice guy. He's never like putting himself in the front. He's up back here. So I have to thank him very much for enabling all this research and heading it also in part. And all the people that are part of the institute here. It's not super up to date. As I've said, it's already autumn here in Germany, so we don't have that much sun anymore. But yeah, it's a pleasure to work with all these people. It's also a pleasure to work with all the people who have helped us finance-wise. And yeah, with that, I want to conclude my talk. Thank you very much for your kind attention. And of course, I'm happy to answer your questions.
Okay, thank you very much, Dr. Michael Gopus. Very nice presentation. I'm sorry, I don't understand about the pronunciation. Is it Michael or Michael in Deutsch?
In German, if you want to have it really complicated, it's actually Michael.
Michael.
Michael, the Emirate, but you can also use the US version of Michael. That's perfectly
fine. Okay. Okay, thank you. There is three big points. First is the effect of support material on ruthenium activity in GA conversion, and then the effect of absorption and diffusion in TS1 is AC composites on methyl OLED epoxidation. And also for the extra chapter, we have alkanes from TCR bio oil with zeolite, alumina, and metal catalysis. Entering the discussion section, I think some audience already have question. So please feel free to ask. You can raise your hand and also turn on your camera. Please. Ya, mungkin teman-teman peserta dari Bapak Ibu ataupun teman mahasiswa boleh bertanya. Silakan.
Rujito here. Misha.
Yes.
Yes.
Maybe I have some questions that can start the discussions. For your first part during the Florian presentations topic, have you ever tried using a bimetallic instead of one active metal like nickel, ruthenium, or other than one metal itself? Because usually bimetallic is much more or enhance more catalytic activities during that hydrogenation process, or?
Yes, it's actually very true. And we did actually do a study, but I didn't show it here, on making bimetallic, so that's a good point. We tried different approaches, and actually combining ruthenium with rhenium was quite successful. There was also some hints about that in literature, so we did that too. What we found out there is two things. A, you can indeed bolster the activity a bit. But B, also it is very important in which sequence you deposit the metals. So I don't have the data here at hand, but it's very important which metal you basically deposit first. And we didn't really have the possibility to investigate in complete detail to completely understand it. But it's obviously important if you make a ruthenium first and then you deposit some rhenium on it, or if you do it the other way around and you have a rhenium layer and you deposit ruthenium on it. It gives a very different activity, and it's usually it was better to deposit the rhenium first. We assume that it is because then we have more active ruthenium surface area. But there is definitely some sort of synergistic interaction between the two, that we can see a slight increase in activity if we go for bimetallic catalysts, like with this rhenium one.
You have feedback?
Nope. Thank you.
Okay, thank you.
Thanks.
Now the audience, maybe?
May I have one question, Aji?
Yes, ma'am, please.
Oh, yeah. Thank you, Michael. Michelle. Am I right, Michelle?
Yeah, that's pretty close. Yes.
Okay. Okay. As I can see from one of your slides, that the apparent conversion always around 40%, even though if we are using the commercial catalysis. Would you please explain why it is always, I can say, less than 50% of apparent conversion? What happened actually? as a kind of poisoning of the catalyst or something else?
Yeah, I meant to jump to the slide, but
I don't remember what number of
yeah.
your slide.
Yeah. Okay,
You compare the apparent conversion between your catalyst and the commercial one.
Yeah, so again, it is assumed that there is some sort of with our composite material, we're actually getting rather close to like not full conversion, but at least 80–90% conversion. It's true that the conversion catalyst cannot do that. So there must be some sort of deactivation phenomena. And we assume it's just that the reactants and all the products are like lying on the active sites or on the external surface of the catalyst and do not allow further reaction. Since we do not observe really very much of like coke formation that you could maybe also expect to be a desactivation phenomena, we don't see that too much. And if we look at the catalyst after the reaction, if we really thoroughly wash it and clean it, it seems to be rather intact. So there doesn't seem to be like big damage to the pore system or the active sites. So most likely it's probably really a blocking of the active sites during the reaction. But we did not investigate that in detail. So this is for now only a research assumption. But thanks for the question. A very valid one.
But I'm not sure the slide is not this one.
Okay, so you meant another slide?
Yeah, another slide.
Something like this?
No, next.
Next. So was it in that? Probably not in the diffusion part. Probably it was in the first part. No, there's not much. Yeah, this is a different way of plotting it. So this is probably not so. Maybe it was here. But here again,
okay, this one.
This one.
As we can see, the apparent conversion is only about 40%.
Yeah, because this system again is very close to the. I mean, the first approach was really taking the TS1 and adding the spherical activated carbon to it, to get like a different reactant system in terms of a composite material. And the idea is that we maybe disperse our crystals much better over the spherical activated carbon. If we just take the TS1, even if we add some macropores, we still have the problem that we just have the crystals in the reaction solution. They will probably to some extent also agglomerate together, and the actual available surface area for the reaction to occur is small, as compared if we basically like we would normally do with a metal catalyst, right, where we use a support. We use the support to finally disperse our metal particles. And in the terms of this composite material that we made, we can in principle imagine that the TS1 is our metal. We want to finally disperse our TS1 particles over the composite material. Here again, it's more like we have an unsupported metal, if you draw the analog to the metal catalyst reaction. And then we always have the problem that maybe with just big bulky molecules, the few amount of active sites of accessible surface area is covered at some point, and so the reaction cannot proceed. That is the assumption why we cannot go to really high conversion. I mean, you can see it's slightly increasing here still, so probably there is still something happening. We could maybe run it for, we did run it for very long times. Eventually, it reaches a plateau. And of course, this is a strong indication for some sort of deactivation phenomenon, but we did not really observe like coke formation or degradation of the active sites, so we assume it to be really covering of the active sites during reaction. But we are not 100% sure what it is.
Okay, thank you for your answer.
Okay, I can see hands from Dr. Hans Saputra and Dr. Yuni. You have question maybe from Dr. Hans Saputra first.
Yeah,
okay.
Yeah, Hans dulu.
Terima kasih. Thank you very much, Mr. Michel. Thank you very much for very interesting presentation. I want to know about how is the stability of catalyst, especially ruthenium in some support that you mentioned, such as titanium, alumina, silica, or activated carbon. Is it supporting for repetitive utilization catalyst? In my experience, for example, for titanium MCM41 structure will damage in extremely low or high pH. I think this is about the stabilization of silica structure. That's number one. And the second question is about the, according to the absorption-desorption graphs, we can see clearly that there is the hysteresis in macropore areas for SAC, but not in SAC. Could you explain more detail about what happened in that materials, especially for SAC materials? Thank you very much.
Yeah. Okay. Thanks. Thanks for the question. So the first question concerning the stability, you're right. I mean, we have to separate the two cases here. The first case where we investigated the ruthenium catalyst, it was in aqueous acidic media, and so we could not use the titanium was quite okay, but the silica not so much concerning the stability. That's why the base case we also used also for the second study was the carbon supporting material, because the carbon, of course, suffers less from these acidic conditions. For concerning the silica and the ruthenium, if we were to conduct some sort of long-term activity studies, we would probably run into problems or difficulties. We didn't though, because we were not so much interested in this case to make a very active catalyst, but we wanted to really understand the role of the support in the activity. Of course, if we now found out titanium is a very active catalyst support, as a next step, we should in principle investigate, okay, how is the long-term stability? What can we do? We did do some work into zeolites for the same reaction media, which are also prone to this kind of dissolution. And we did do some work also that has already been published on the conservation of stability. Strategies there involve hydrophobization of the surface by basically taking the OH groups that are at the surface and putting a alkyl group on it so that the surface gets more hydrophobic and is less prone to attack by water. And another thing that we did is we added, and that again is for zeolites, not for this very case. So we would, for titanium, look into it again by adding lanthanum to the zeolite structure. That also is known from literature to increase stability. That's also an approach. But of course, lanthanum is very expensive. We would have to look into that, but it was not so much the focus of the study. Concerning the second question, option. This is not, this is the part. What we would normally expect, I mean, first we have the
No, the previous slide.
The previous?
SAC of absorption desorption curve.
Option D. I'm not 100% sure whether I know what you mean here.
Yes, this one. Yeah.
Okay.
Yes, this one.
Yeah. So basically, what we see here is this what we see here in the region of higher pores is basically contributed from the activated carbon. So we have an activated carbon that already has a given pore system, and that is rather heterogeneous. As you know, it's a commercially produced activated carbon. So they take the carbonaceous species and steam it with some sort of procedure. We get it from a commercial partner, and it already has like a pore system that looks like this. So you have some amount of micropores there, few mesopores, and yeah, some bigger mesopores to macropores. Of course, we know that we can't really trust the nitrogen absorption so much for pores that are bigger than maybe 50 nanometers, because the Kelvin equation doesn't really hold true. But we do have some mercury intrusion results as well. And it suggests to us really that this carbon, that is basically our base material, what we make the composite from, it has a given pore system of really this different types of pores. I think maybe even in the supporting material I have a more detailed. Let me see if I can find it quickly. I did sort into some amount. Pretty sure I put some. It's maybe not the finest analysis. Let me show this. No? Okay. So basically, maybe I'll just explain it as is. Basically, what we think we're seeing is oh, I lost the slide again. What we think we are seeing is what we think we're seeing is that we have this initial pore system, and then we add the TS1, which has the yellow initial pore system. So if we were just putting them together, right, if we would make a physical mixture, which we also did for catalytic experiments, what we would expect is that we get basically only a linear combination of these two, right? We have this pore system and we have this pore system, and then we just take the two and put them together, maybe 50-50, then we should really get something that is in the middle of this. But what we actually, and we see something like this, right? I mean, it is somewhat in the middle point. This is about 50-50 mixture here. It has 56% of TS1, and then of course 44% of the SAC, and it looks like somewhat of a mixture between the yellow and the black one. But it's more than this, because when we make the composite, we're actually doing also something to the pore system of the SAC catalyst, and we're blocking some of the pores, and that's why it's more than a linear combination.
Okay.
Does this answer your question? I'm trying to jump to the additional materials where I do have something about this.
Okay, thank you very much. Terima kasih, Bu Pit.
Yeah, you can somehow see it. Maybe coming back to this really quickly. For width distributions, that we have this big mesopore area here of the SAC that we kind of, if we go from the black to the green dotted one, that we kind of block. This is kind of a pore width that we block. And of course, we do have, in principle, both pore systems that are in the parent materials available. So we have the TS1 pores, and also in the composite materials, a bit shifted here. And because these are the intercrystalline, so that is the between the TS1 crystals, so they are existing as well in the pure TS1 as well as in the composite materials. And the black one is the pores of the carbon, and we cover some of the medium-sized mesopores in the carbon due to the deposition of the TS1 crystals. If you imagine this picture that we draw, where we basically had the circle, and then in the circle and the pores we had some of the crystals, that is basically reflected by this reduction in pore width or commutative pore volume at this pore width here. And of course, we always have the micropores of the TS1.
And
Okay, I hope.
Okay, thank you. Maybe for the next question, Dr. Yuni Krisnandi,
Yeah.
please.
Okay. Thank you very much. It's very interesting talk, Michael. I just wonder. This is just general question that I wondered. You have special reason that you skip mesoporosity. You jump from microporous to macroporous. I just wonder whether there's the reason, because you deal with biomass as a substrate, so you need such a bigger pore for access, and then this, because the active site still always resides in the microporous. I just wonder if that is the reason. And then usually it is interesting that usually in photocatalysis that we think about this, look carefully for the absorption activity, whether it is real photocatalysis or it is also absorption. But you also here consider this absorption will affect the result of this catalytic activity, because in heterogeneous catalysis, in theory, we need this absorption on the surface of the catalyst. Yeah. Then we can expect that the process will take place, like for example, the extraction of the CH bond, for example, or the hydrogen dissociation, etc. We expect that it will take place on the surface. That's why we consider we need this absorption. But in this case, it is interesting. I think it's very good to study this as well. That you also remind us that the absorption could be also not as good as it thought. I mean, it's too much. Yeah. So I just wonder to what extent actually this absorption needed in this heterogeneous catalysis. I know maybe it's beyond this project, but overall, it seems that we need to consider this absorption of activity in the heterogeneous catalysis. That's all. My question. Actually, I have a lot of questions. I mean, your talk is really entertaining for me. It's really very good. Yeah, I really enjoy it. Yes.
Well, thank you very much. Maybe let me start with the second question. Yeah, it is true. Yeah, I mean, we as the heterogeneous catalyst scientists, we need absorption, of course, to get some reaction. But yeah, it can also be a pitfall. I maybe have to. I mean, I don't want to like dilute my message here, but I have to say that for technical reasons, we have to work in this reaction with rather low concentrations. And of course, the lower you go with the concentrations, the more important this effect becomes. Because if you have a decent amount, or like if you have more adsorption sites than you have reactant molecules, then of course this effect is very strong. But it's usually not the case and it's also not the case in our case. But we are working at rather low concentrations, and lower the concentration, of course, and with this amount of reactant molecules compared to the adsorption sites available, this effect becomes more and more important. Usually, for example, you have the same thing if you do photocatalysis, where you usually also work with very low concentration. And especially if you do that, taking a more careful look at adsorption is very important, because we also do co-photocatalysis, and I know that from there as well. Yes, but yeah, of course, it's always a trade-off. We want some adsorption. That was also why we did this synthesis strategy in the first place. We thought like, okay, yeah, we want the molecules to adsorb in the vicinity of the active center, so let's make this kind of composite material. And it did have some benefits, but seemingly the benefits work out different than we thought in the first place. It's nice that we have the benefits, but of course, as scientists, we also want to understand what's happening. And it seems to be a bit different than we initially thought. Although the strategy seemed to have yielded us a good catalyst, it didn't exactly work as planned, I would say. And the second question with the mesoporosity and the macroporosity. I mean, maybe it was not made very clear. I mean, we tried the mesoporosity as well. It is basically just building up on synthesis strategies, right? You start out with your zeolite, which only has your micropores, and you know, okay, obviously you have some property mass transfer here. In this case, the molecule cannot even go in. So there is like even commercialized strategies, I think, these days to introduce mesoporosity via alkaline, and that is very relevant. You can do that. And you get somewhat, usually, I mean, this is here maybe not the best case. I mean, you can maybe see some increase, but this is maybe, we have to look at our experimental data very carefully, whether this is significant and where our error is. But we can maybe see an increase in activity. But this mesoporosity also has some drawbacks. For example, the conventional industrial treatment to make them mesopores. We tried this as well, and we tried to reproduce some procedures, and it in general works. But what the people don't tell you oftentimes is that you start with 1 gram of catalyst, then you do the treatment, and then you have 0.1 gram of catalyst, which has the mesopores. So yeah, you do get your mesopores, but you do lose also quite a lot of catalyst, and that is of course detrimental. This kind of macroporous bottom-up kind of synthesis strategy may be more efficient in terms of conserving the material and still getting a rather active catalyst. Again, this is all work in progress. I wanted to show you like what we're doing right now. If you want to look into the publications, then you can see what we're doing in the past. So yeah, we do not completely understand them yet, but yeah, I think that's a strategy we're trying to take to get more.
Okay, thank you. Yeah, I hope that through Bu Witri, maybe we can keep in touch and continue, perhaps Bu Witri, with nice collaboration in the future, Bu Witri. Yeah, I'm looking forward to it. Yes,
Dr. Yuni want to collaborate with your group, I think, because the research is very close with the area of Dr. Yuni's research. Yeah?
Thank you very much. Yeah.
You know, we don't exclude MOFs, you know, that we can also do some catalysis with them. So
oh yes.
But yeah, we're more working in zeolite.
Yeah, thank you so much. But I'm afraid with the
Dr. Yuni are working in the in the zeolite area. Yes.
Zeolite area and also catalysis.
Yes.
Okay, thank you so much. I'm afraid I have to go. I have to teach at 3 o'clock. So yeah. Thank you again for the nice talk, Bu Witri. Thank you for inviting me as well to attend this very nice international guest lecture. Pak Hen, ya.
Terima kasih Bu Yuni.
Ya. Oke, Assalamualaikum.
Waalaikumsalam.
Selamat mengajar.
Okay, thank you, Dr. Yuni and Dr. Hans Saputra as well. Maybe for the next question, come from student, maybe. Don't worry. Please feel free to ask.
Student, if you want to ask in Indonesian, please. Yeah. And Misha, I have a short question, Misha, related to the biophotoCatalytic action in algae. Could you tell us how is the experimental design? How do you use this sunlight and then connect it to your reaction system? How to manage this one? Because this one is very interesting in Indonesian area, because we are very rich with the sunlight, and we can apply this in our lab maybe.
Yeah, I did not talk about this in this study because I tried to focus on the polymer thing, but of course we do some photocatalysis as well, and we have a setup. I don't know whether I can find this super quickly. In principle, we have a sunlight simulator that is irradiating. So we have a kind of like a reactor that's shaped basically. Oh no, it's killing the mud out of the picture. So it's shaped like a mud, the reactor, and the sunlight simulator is on top. It irradiates on top of the thing, and in here in the mud we have basically a stirred reactor, and we have gas in and gas out, and we kind of like pump in the setup. We pump the gas phase around, and it always goes through the thing and then out again, and through the thing and out, and it's connected to a GC. So every now and then you can take a sample to the GC, and then you can analyze the gas phase. And of course, we can take liquid samples to analyze from the liquid phase and do some GC analysis or something like that. But the advantage is really the sunlight simulator. I think that the idea of having a reproducible light source is a very important one, and it's an idea that is somehow like going or penetrating the scientific community in the photocatalysis, because it's really hard to reproduce the works of other people if everybody uses a different light source and different experimental setups and all these kind of things. So it's very, very important to, if you don't have to, of course it's expensive to buy such a thing, But if you don't have the resources to buy such a thing, then at least you have like a very thorough description of your experimental setup and you give a spectra of your lamp. But we are fortunate enough to have such a solar simulator, and when we have an apparatus that is connected to it.
Okay, yes. Nice.
Okay, yeah, if you need more details, please contact me later. Yeah, we do have, I do have a presentation about this as well, of course, and there is the experimental setup also given, but I don't have it. I mean, I do have it here, but I think it would take too much time to open it.
Thank you.
Okay, thank you. Maybe another question from student, maybe. Okay, may I have question, ma'am?
Yeah, the last I think
I'll-
because the time is already long. Yeah, the last question for Maci.
I want to ask Dr. Mai Misael Gupel, is there any opportunity to ask students from Indonesia to go abroad and study in Leipzig, maybe?
Yeah, I mean, you can of course turn to Vitri and the uni, if I got the name correct, who was in the LICAT. I mean, she obviously made the experience already. What I can, from the top of my head, say to you, yeah, that there is this Erasmus, basically this Erasmus Plus, I think, mobility grant that is, and then there is the option to go via DAAD.
DAD, yes, DAD is open now in October, I think. In October will open.
They are opening scholarships. Usually this works like this, that it's usually for PhD, and it usually works like this, that you have some idea of what you want to do, and then you contact us.
Yes.
And then you, for example, you have like some sort of research plan and you show it to us, and then you can say like, okay, yeah, this makes sense concerning the equipment that we have and the possibilities. And or I would maybe modify it like this, and maybe we can also help you with some of the expertise we have in writing these proposals. We cannot write it for, but we can help. Designing it, and of course also fitting it to our possibilities. And then you can apply for DAAD scholarship. And then of course it's with the DAAD whether you get it or not. And if you get accepted, then you can get the salary basically from the DAAD. Sometimes you get a small amount of euros basically to buy some chemicals, sometimes not. And we can also provide some amount of chemicals. We can provide you with a workspace and infrastructure. That's something we can give. And yeah, and you have basically the scholarship. That is the traditional way people from abroad come to our group. And we do actually have quite a few on this kind of. At the moment, there's Rito, there's Adrian, there's Hasib. So we have at least 3 students at the moment who came to our group via this means. So it's definitely a viable means.
Okay. Thank you. Maybe that's all. Yes. Thank you very much for your coming and also for your presentation. It's been very nice. And for the last section, maybe we can take some photo. Dr. Misael, you can turn off your share screen before.
Yeah, wait. Yeah, I will.
Audience, may you turn on your camera, please? We can take some photo.
Yeah.
Okay. Okay, it's already. All right. 1, 2, 3. Okay. Another photo again. Okay. Okay. Ready in 3, 2, 1. Okay. Thank you very much. Thank you very much. Thank you.
Anci. Maybe you can share the certificate, Anci.
Oh yes, all right.
Yeah.
So we have another guest lecturer.
No, not
Who's
this,
out?
not this. The certificate.
Okay,
The certificate.
wait.
Certificate.
Yes, wait. Okay, Dr. Michelle Rupel, this we have certificate. Fitria maybe.
Yeah.
Apa ya, memberikan
Thank you
sertifikat.
thank you very much, Dr. Michelle Kupel, for your lecture today. And here is the certificate of appreciation from us. And
Thank you very much.
yeah, it is a
That's all.
pleasure to know that there are many people who are attended this meeting, whether from student or other college. I can see there are many lecturers like Professor Hamzah from ITS, Ibu Nurul from ITS, Bapak Hans, UI, Ibu Yuni. Thank you very much for your coming. And I hope that through this meeting, we can share our knowledge and also we can continue our network, whether in collaboration for research or chemical education or joint publication maybe. Yeah. Thank you, Dr. Michael, once more.
Thank you for having me. It was a pleasure.
Yes. I will send by email, yeah, Michelle, to this certificate of appreciation.
Yeah,
Yes.
thank you very much. Always a pleasure.
Yeah, Dankeschön. Okay. We also have another agenda. This is another this lecture. Audience, please note the date and time. You can also join the next
Will be
guest lecture.
next week, yeah.
Yes, next week.
Yeah, will be conducted on October 7. Professor Nikolai Lehnert. He is also a collaborator of Dr. Witri Wahyu Lestari. So the topic of lecture will be still on the catalysis, yeah, Bu Witri.
This is like
no.
signaling.
Yeah, signaling.
Signaling, yes.
Coordination and bioorganic chemistry.
Okay, thank you all for today and sampai ketemu lagi di lain kesempatan. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you for coming, yeah, Ms. Shail. Thanks for the knowledge.
Thank you for coming.
Yeah, it was a pleasure. Bye-bye.
Bye-bye.
Bye.
Terima kasih Bapak Ibu semua. Ibu Ati dari Unpad, Bu Nurul dari iya, Pak Hamzah, terima kasih kehadirannya.
Sorry.
Oke, Prof. Hamzah, Bu Nurul, terima kasih juga kehadirannya.
Mantap, hebat lah. Beres, Bu Fitri.
Amin.
Semangat. Bu Fitri
Semangat,
juga.
Semangat. Terima kasih.
Terima kasih Pak Hans. Terima kasih Pak Hans
Saya pamit
kehadirannya.
ya. Nah, nanti yang berikutnya tanggal berapa tadi?
Tanggal 7, Prof.
Tanggal 7.
Tanggal 7 ya, 7 Oktober. Oke,
Prof.
Mohon diingatkan ya Bu Witri ya.
Siap Pak. Siap Prof.
Kalau jauh-jauh hari itu nanti malah tambah. Hari ini kemarin di mana gitu ya WhatsApp-nya.
Harus aktif memang ini.
Ya, Assalamualaikum.
Waalaikumsalam. Terima kasih Pak Fajar, Prof. Edi Heraldi, Pak Hans, terima kasih.
Ibu Fitri, izin live.
Ya.
Bu Fitri ya, saya izin live juga nggih.
Ya, monggo silakan.
Terima kasih Bu sudah mengadakan guest lecturer.
Ini recordingnya di Zoom 35 ya? Tadi yang record? Aji yang record?
Bukan Bu.
Yang record siapa?
Siapa tadi ya?
Ya sudah, di stop dulu aja.